Today I'll be working through question 3 from the Physics 457 practice final exam in preparation for the upcoming final in April. Question 3 asks, given the potentials listed below, which are in the Lorentz gauge? The Coulomb gauge, neither, or both? And you have to explain how you know. And you have to find the electric field and the magnetic field after you've determined which gauge the potentials are in. And there are suppressed units to make sure the expressions work out for all of the problems, so we just don't worry about the units. And then there's two different types of potentials, the first potentials and the second one. So we'll work through the first ones first in this first video and calculate E and B, and then we'll do the second ones in the second part of this video. So this is question 3, part 1, and we see that we have the potential V, R, theta, and T, and that's equal to negative Q over R, and we have the vector potential on R, theta, and T, and this is equal to negative QT over R hat. So again, this is the vector potential, so we need a vector quantity as well, direction, and then V is just the scalar potential. And we want to say what gauge are these potentials in, and then show our work. So we can recall that we're looking for the Coulomb gauge and the Lorentz gauge. So first off, it's good to note what those two gauges imply. So the Coulomb gauge suggests that the divergence of our vector potential is equal to 0, and the Lorentz gauge suggests that the divergence of our vector potential is equal to negative epsilon naught mu naught dV by dt, the change in the scalar potential with respect to time. Change my pen here, so that one's dying. So to check these gauges, we need to calculate the divergence of A and the divergence of A and see if they're equal to 0 or if it's equal to the negative time derivative times some constants with respect to the scalar potential V. So we'll start with, here's our vector potential, and we'll start with taking the divergence of this. The good thing to note right away, which I will say at the start of this video, is that the coordinates that we see here are spherical. So that means that we take the divergence, it's going to be in spherical coordinates. And that's important so that we know that when we use the divergence formula from our formula sheet, we want to take the divergence in spherical coordinates. And right away we can also see that this only has an r hat component, so that will simplify that operator, the del operator that we use for that divergence term. So we can see here that this is simply the divergence of negative qt over r hat, and using del from spherical coordinates, we see that we get 1 over r squared d by dr r squared times negative qt over r. Make sure all the brackets are in the right spot, plus 0 for the other two components of this divergence, because there is no other theta hat or phi hat component. We're in spherical coordinates. So taking these derivatives, we get 1 over r squared, and we see that we have an r squared that cancels with this r on the denominator. So we take the derivative of that with respect to r, we just get negative qt over r squared. So the divergence of A is equal to negative qt over r squared. Negative qt over r squared. So we can see right away that this does not equal 0. So we are not in the Coulomb gauge, not in CG, not in the Coulomb gauge. Now additionally, we want to check to see if we're in the Lorentz gauge. So we can do this by taking the time derivative with respect to the potential, which is given by dV by dt is equal to d by dt of our scalar potential, which is negative q over r, and we can see that this is equal to 0. So the divergence of A, which is equal to negative qt over r squared, does not equal negative epsilon naught mu naught times 0. And so we're also not in Lorentz gauge. Not in the Lorentz gauge. So we've determined that we're neither in the Coulomb gauge nor the Lorentz gauge. And that's part A of the first part of this question. And the next thing to do is calculate the electric field and the magnetic field. Now, part B asks us to find the electric field for this configuration of potentials, and part C asks us to find the magnetic field. So we'll do them simultaneously. So in order to find the electric field from these two potentials, we want to recall that the electric field is given by the negative gradient of our vector potential minus the time derivative with respect to our vector potential. And that's a formula that's probably in your formula sheet as well. It's just good to know that the electric field is given by the negative of these two, potentials. This is the gradient, and then this is the time derivative. So in order to do this, we just simply have to take that gradient of v, and again, we're in spherical coordinates, so we only have to worry about the r component. So we have negative d by dr of our scalar potential, and then this will be in the r hat direction, and then the other terms and that are 0. And then we subtract off the time derivative of our vector potential, negative qt over r hat. So we can do this derivative through, and we get the negative and the negative cancel, but we get an additional negative from the fact that we do a derivative with r on the denominator. So we get negative q over r squared r hat from the derivative. Again, the negative and the negative will cancel, and we get a negative qt. So I'm taking the derivative here with respect to t, not with respect to r in this case. So the negative and the negative will in fact cancel, and I take the derivative with respect to t of this expression here, which gets rid of the t in the numerator, and I'm left with q over r with the positive sign in the r hat direction. So you take the derivative with respect to the time of this vector potential, not with respect to space like you did for this gradient here. So we're left with the electric field is equal to negative q over r. I can factor that out, and I end up with a 1 over r, a negative 1 over r plus 1 r hat. That's my final expression by pulling out a negative q over r in this case here. Make sure I did that factoring correct. This negative sign would actually be on the 1 here. So I have a negative q over r pulled out from here, so I'm left with positive 1 over r, then minus this 1 by taking out negative q over r there. So that's our electric field. Now the magnetic field, let's do it over here, is given by the curl of our vector potential A. And again, this curl will be in spherical coordinates, which is that big long gross formula that we all love on our formula sheet. So we have 1 over r times 1 over sine theta d by d theta minus qt over r. And this is in the theta hat direction. So I've taken this formula as part of the curl formula from your formula sheet in spherical coordinates. However, right away we can see that there is no theta dependence here, so this derivative is going to go to 0, and our magnetic field is simply 0. So again, we just have to recall that the magnetic field is given by the curl of our vector potential A, and because our vector potential A is in spherical coordinates, we take this curl in spherical coordinates as well. You have to pick off that component from your formula sheet of the spherical coordinates curl formula, and then you find out that because there's no theta dependence here, this derivative will go to 0, and left with the magnetic field is equal to 0. So for these two potentials, we see that the electric field is given by negative q over r, 1 over r minus 1 r hat, and the magnetic field is 0. So continuing on with the second part of question 3, we have two new potentials. Here we have the scalar potential v. It's a function of s, phi, and t. It's in cylindrical coordinates, and that's equal to negative t times phi over s. And our vector potential A is, again, dependent on cylindrical coordinates s, phi, and t, and that's equal to phi over c squared in the s hat direction. So again, I mentioned that twice, one for each of these different potentials. We are in cylindrical coordinates. So all of our operators will be acting in those coordinate system. In that coordinate system. So we want to check the two gauges. We're seeing for the Lorentz gauge or the Coulomb gauge. Again, we want to recall that the divergence of A, when that's equal to 0, then we're in the Coulomb gauge, and when the divergence of A is equal to negative epsilon naught mu naught times dV by dt, then we're in the Lorentz gauge. So we calculate divergence of A first, and again now we are in cylindrical coordinates, so our divergence will utilize that formula, and we'll have 1 over s d by ds of our s multiplied by our A, which is phi over c squared. and this is given by 1 over s times phi over c squared. So we see that it's not equal to 0, and therefore we are not in the Coulomb gauge. Now we can check also our time derivative of our scalar potential, and we see here that we get d by dt of negative t phi over s, which is equal to negative phi over s. So this is not equal to 0, so that might be some indication that we might be in the Lorentz gauge. So if we multiply dv by dt by negative epsilon naught mu naught, then we'll get negative epsilon naught mu naught times the negative phi over s. And we see, if we recall that epsilon naught times mu naught is equal to 1 over c squared, we end up with s over c squared. And we can see that our divergence of A is equal to 1 over s times phi over c squared, and that our negative epsilon naught mu naught times dv by dt is also equal to phi over s times c squared. So we have that the divergence of A is equal to negative epsilon naught mu naught dv by dt, and so therefore for part A we conclude that we are in the Lorentz gauge. And again, we saw that because the divergence of A was not equal to 0, so we are not in the Coulomb gauge, and the divergence of A is equal to this constant, and then when we solve through for dv by dt and multiply it by negative 1 over c squared, so epsilon naught mu naught is 1 over c squared, then we end up with the same constant. Okay, now part B, we want to find the electric field. And again, we recall that this is equal to the negative gradient of the scalar potential, subtracting off the time derivative of our vector potential, which is here. Now we are in cylindrical coordinates, so we want to use the gradient in cylindrical coordinate space. And we will see this is going to be negative times d by ds of negative t phi over s, which is our scalar potential in the s hat direction. And then that is also adding on a 1 over s d by d phi of negative t phi over s in the phi hat direction, as now our scalar potential depends on both phi and s, so we will have two terms when we take that gradient. And I'll make sure I got that right. Yes, those are right. And this will also be subtracting off the time derivative with respect to A, but we can see right away that A has no time component, so that will just be equal to 0. So this d by dt of A is 0, so I'm not going to include it here. So we'll take the derivative with respect to s of this. I'm going to get a negative 1 over s squared. The negative and negative will cancel. The negative on the outside adds in, so we get a negative t phi over s squared, taking the derivative with respect to s of this first term in s hat. And I add on, and again, now I have a negative here, but that negative will cancel with the one outside here, outside the brackets, and I get a plus 1 over s squared t, because the d by d phi of the phi hat term will go away, and I get a phi hat there. So check here, I'll have t phi over s squared s hat plus t over s squared phi hat is our electric field. So again, all I did was take the gradient of the scalar potential in cylindrical coordinates, and I know that the time derivative of our vector potential will be 0 because there is no time dependence here. Doing those derivatives, you get this electric field. The magnetic field, again, is given by, change my notes here, it's given by the curl of our vector potential A. And again, now we are still in cylindrical coordinates, so we want to use the curl in cylindrical coordinates, which the only term that survives from that, you can check on your formula sheet, from that curl is d by dz of phi over c squared, and that's in the phi hat direction, plus a 1 over s negative d by d phi of phi over c squared in the z hat direction. If I can squeeze that in there, negative c, oh sorry, not negative, c squared on the denominator. Okay, so this is the curl term. We have a d by dz term of our magnitude of A, and that will come off in the phi hat direction, and then we have an additional curl term, which will be 1 over s negative d by d phi of phi over c squared in the z hat direction. So doing those curls through, this is 0, so we end up with negative 1 over s c squared in the z hat direction. And again, we're just using the curl formula in cylindrical coordinates, so that this operator, the curl of the del operator in cylindrical coordinates, and that if you plug in your function for A into that, you'll end up with the magnetic field is equal to -1 over SC squared in the Z hat direction. So for this problem we have worked through, we've taken the two potentials, we've used information to determine what gauge those potentials are in, the Coulomb gauge or the Lorentz gauge. We've determined that it's in the Lorentz gauge because the divergence of A is equal to the -1 over C squared multiplied by dV by dt, the derivative at the time of the scalar potential. It's not equal to 0, so it's not the Coulomb gauge. And then we found the electric field and the magnetic field just by doing a little bit of operations using the gradient and the curl. And that is the solution to question 3.